Okay. So we can.
Today I give the second part of the lecture I gave last time. It was about discretization of diffusion processes using Monte Carlo methods. So this is a very classical lecture. Maybe I can just recall very briefly what we did last time. Last time we considered this classical SDE. S T equals sigma ST dW T plus mu ST dt, where the initial value is given. Okay, so this is very classical. Sigma is mapping from RD into the set of matrices R D times M, mu from RD into RD, and W is just Brownian standard to Brownian is standard Brownian motion. So we complete probability space. So this is the classical setting. As usual, we have supposed that there exists, so this is an assumption, hypothesis. There exists a case triple positive, so that actually the coefficients mu and sigma are globally Lipschitz. That is the number of sigma x minus sigma y, etc. So same thing for mu. As than k times the norm of x minus y. So this is what we have studied last time. And the idea was to simulate this, the solution of this SDE, okay, which represents the price of some scheme assets. S is a vector value, the dimension of S is D. Okay. So we have to do so reduced to the earlier scheme. Precisely, precisely we introduce the discrete times Ti n equals capital T over n times I, because we consider a time interval 0 capital T, and then we consider this uniform discrete times from I equals 0 to n, and then we introduce this scheme Sn 0 equals S0, the initial value, and then inductively we define Sn Ti as Sn Ti minus 1 plus extension of this coefficient, that is sigma Sn Ti minus 1 delta W Ti plus mu Sn Ti minus 1 delta Ti. This is very classical. This is a classical discrete layer scheme. Associated to this scheme, there is also a continuous, so associated to this scheme, there is a continuous version of this scheme, denoted by S hat n, precisely for every t belonging to the interval ti minus 1 ti. Of course, you know this notation. This is the increment wti minus wti minus 1. Same for beta ti. Here, for every t in this interval, we define s hat n t as s n ti minus 1 plus sigma s n ti minus 1 times wt minus wti minus 1. Actually, we want to join the points s n t minus 1 and s n at time t n by a continuous process through the Boolean motion and the function, the identity function time. Okay, so you just write this this scheme. And you observe that actually these two processes coincide at the discrete times, discrete dates ti. Okay. So actually, initially, this last time we saw that many we have introduced this continuous version just to get estimations of what we want. Precisely, we want to show and we want that this process be an approximation of our solution. And to show this, we need to use.
Thus, S hat at points t, I coincides with S m.
Exactly, at each discrete time. So that means that when you want to compare actually S with Sn, we can precisely compare S to S hat n. And this is very convenient because this one is actually continuous. In particular, it admits it is the solution of a stochastic differential equation of this form. Precisely.
So you are going to compare the solution of this equation with S hat.
Exactly.
And then S hat with this.
Yes, and this is easier actually. Because finally, when you simulate, want to simulate some trajectories, approximated trajectories of S, we can just do it at some discrete times, Tin. So you don't mind about the value of this process, except at the discrete times. But this is very convenient because it's easier to compare this process with this one, because this one satisfies the stochastic differential equation. Precisely, we can write things like this. ds hat n t equals sigma s hat n. You can write k. I don't remember last time how I wrote the thing. Kn t. Okay, this is here. This is the largest Tin before T actually. dwt plus something for the drift. Okay, and of course knt. It's just t I minus 1 n on ti minus 1 ti. This is now we can compare them, and because of the Lipschitz coefficient, when you want to estimate in the mean square error actually between this process and this one, then you can use classical techniques from Monte Carlo methods, in particular Rondois-Lemar, Cauchy-Schwarz inequality, etc. Okay. This is the idea. And so the main result we have seen last time is actually you can say that the expectation of the supremum of the whole t less than capital t of s t minus s hat n t also this our p our one over p, it is LP norm, is less than some constant depending on the coefficients on the t also. So if you consider an infinite horizon, this is very different, more difficult actually. Here it depends on t, and generally you have a term which explodes with respect to capital T. Over the square root of n. This is a classical with
For any p?
of course,
C depends on p.
Of course,
C depends on
of course, capital T, P, and the parameters
for example,
also is D.
Okay.
This is the main result. So we have shown this result in particular. Today I want to talk a little about the Milshtein scheme, and afterwards I'm going to talk about an application of this result, because we have already seen the last time applications of these Monte Carlo methods, that is how to deduce the pricing of European claims. Okay, so today I'd like to talk about barrier options, because we're going to use specific techniques, in particular based on Brownian bridge. But before this, let us talk about the Milshtein technique. Okay, so what is my is okay. What is my notion? Okay, so this is the fourth part of my lecture. So Milshtein scheme, which is a method to improve convergence rate. So we need to understand how, actually in general we just obtain convergence weight which is of the order square root of n, and then if we want to improve this convergence weight, we need to understand what it is the best to do to improve it. Actually, if there is an error in the approximation, this is due to the fact that we approximate the volatility by this, and the drift by this. And so the interesting question is whether by which way we can improve the convergence weight, either by modifying this this approximation or this one, or maybe both of them. Okay, so have a look. Let us have a look on this. We first consider, for the sake of simplicity, the case where d equals 1. It is a real valued process S, because in general it is a vector valued, okay, process. And then in the Euler scheme, we have approximated integral from ti minus 1 to ti of mu su du, Okay, this is the integral comparing the stochastic representation of the solution to the DD. Then we have used the fact that actually this integral may be approximated by mu STI minus 1 times delta Ti, just because mu is continuous as a Lipschitz function, as well as S. Okay, and when you use this approximation, we need to control the error. And here, the error is bounded, at least in L1, but actually we can generalize this to any LP by the expectation of the absolute value of the integral from Ti-1 to Ti of mu Su du minus this difference. Of course, you can rewrite it like this. Okay, so that using the fact that mu is Lipschitz, you get that this is less than some constant, say k, times delta t. Just one more step. Integral from Ti minus 1 to Ti for the expectation of absolute value of Su minus S Ti minus 1. Okay, du. But as we have already seen last time, we can easily get a bound about this difference for u between Ti minus 1 and Ti. Okay, and precisely we get that this expectation is less than some constant times square root of delta Ti. Okay, actually you can see this because the expectation of the supremum of Su power what you want is finite, and then use the Cauchy-Schwarz inequality as well as the Ito formula. You just have the square root because of the Ito formula. Okay, because of the stochastic integral. And then you get here that is less than constant time n powers we have. Okay? Because of this. Okay. Now, if you do the same thing but for the diffusion coefficient, what do you get? In this case, similarly, you compute expectation of the integral from Ti minus 1 to Ti of sigma Su minus sigma Sti minus 1 d, this is sign dw, okay? And then using the Cauchy-Schwarz inequality and the Ito formula, you get that this is less than some constant. You don't mind about this constant, except that this one does not depend on n. Times the expectation, square root of the expectation, this integral from Ti minus 1 to Ti, okay, you use the Cauchy-Schwarz inequality. This one, okay? Okay, so now you use the itosometry and you get this. So we get that this is some less than some constant time. Here we get less than some constant time over n, because of the square. So finally, because of the square root, you get this. So clearly, if you want to improve the convergence of your scheme, it's preferable to focus on this term instead of this one, because here the error is less. Okay? So this is what we propose in this Milshtein scheme. So instead of the approximation sigma of SU approximately equals sigma of ST-1, we write the following. Sigma, of course, if U belongs to Ti-1 Ti, depending on the n, sigma of SU, we do not use this, but use a first order Taylor approximation instead of 0,1, actually. That is, we write first SU as STI minus 1, because we call SU the solution of an SD, plus the remaining part, the difference integral from Ti minus 1 to Ti of sigma S R dW R plus a priori the same thing about drift term. Here you have this for the notes is an equality. At this stage, sorry, there was a mistake, of course. U, okay. At this stage, this is an equality, and now we're gonna approximate this term. That is, repeat this procedure, but for this term. By this, there are two terms, and as we have already seen, this one should be negligible with respect to this one. Okay? So what we do is the following. We say that it is approximately equal to sigma of STI minus 1 plus sigma of S at time Ti minus 1 times U minus Ti minus 1. Okay, this is the idea. Of course, we could add another term, for instance, mu of this. Okay, here we just say, okay, for R between Ti minus 1 and U, this coefficient approximately equals. Sorry, there is a mistake.
W.
Okay.
And again here.
Okay. And there's something here. We only keep the main term. From there, because we can now work with a coefficient which is differentiable, we can pursue our reasoning and finally approximate this by sigma of STI minus 1. This is a term actually you have in the initial layer scheme, plus a second term, which is the first or the term of the Taylor approximation, precisely sigma prime of this initial point sti minus 1 times the increment, that is sigma sti minus 1 times w minus wti minus 1. Okay? That is this simple idea. Once you have chosen this way of doing, then you can approximate the integral of this diffusion coefficient between ti minus 1 and ti. This is what we want to do as well as for drift. Precisely, now we approximate the integral from t minus 1 to ti of sigma s u dw by the integral of this. Precisely, the first term is the term that you have in the classical Euler scheme, that is this coefficient times the increment of the Brownian motion, plus the integral of this. Okay? But plus, so when you compute the integral of this between ti minus 1 and ti, you first get sigma prime sti minus 1 sigma sti minus 1 times, so the integral between ti minus 1 and ti of w minus w ti minus 1 d w, and this is a classical result. This is v, whereas integral from ti minus 1 to ti of w minus wti minus 1 dw. This is a classical result which is very well known generally from 0. But of course, this is something, it is a Brownian motion starting from ti minus 1. Okay? So, this result comes from the integration by part formula. So you get the half delta w ti square minus half delta ti. Okay? Yes. Can obtain this result otherwise, if you remember. Can write general xy equals x minus dx plus y minus dy. This is a very general formula, but from there you cannot get what you want. Because of this, in particular, you have a formula for d of x squared. That is twice x minus dx plus yes, this is exactly this, plus d of xx, and then you can integrate and get what you want. Here, I guess this is, yes, because multiply here by 2. Okay? And then, okay, so because of this, now we can write the modified Euler scheme associated to this idea. Precisely.
And this is Milshtein method.
Yes. So the Milshtein is the following. For d equals 1, precisely Sn0 equals S0, and inductively Sn ti equals Sn ti minus 1 plus for the drift, as usual, plus we follow this approximation sigma of Sn Ti minus 1 times delta Tin, sorry, because of room, let's see, plus sigma Sn Ti minus 1 times increment of the Brownian motion delta Wti, plus this multiplied by this. Okay. So half sigma prime, of course, provided that sigma is continuously differentiable. Of course, we need to impose some differentiability conditions. Sigma prime Sn Ti minus 1 times sigma Sn Ti minus 1 multiplied by this joint delta Wti square minus delta Ti. Okay? And more generally, we can generalize this in the bidimensional case. More generally, for an arbitrary D, the Milshtein scheme is the following. Sn Ti equals Sn Ti minus 1 plus the drift times delta Ti plus sigma Sn Ti minus 1 is the same beginning. And then now we need to take into account the different quadratic terms, so that you get the following: the sum of all g, k, and of gradient of sigma dot j. So you need to take into account the different partial derivatives of sigma whose value whose value is matrix. Okay. Times of Sn Ti minus 1. Here sigma dot j means just the jth column of the matrix sigma, times sigma dot k of Sn Ti minus 1. This is the same idea, except that it's more technical to write. Okay? Because S is a linear combination of the components of the standard Brownian motion. Okay. Times the integral from Ti minus 1 to Ti of Ws j minus Wj Ti minus 1 the W sk, and this, of course, kind of term comes from the approximation of the diffusion. But each line actually of the diffusion. This is what kind of combination. Okay, this is the idea. Actually, learning these schemes. But here, the difficulty is that for j different from k, you cannot a priori know how to simplify this in general. Actually, because of this of these coefficients. Because actually, if you want to gather the symmetric terms, because there are some symmetric terms, if you change the role of G and K, okay, if these symmetric terms are the same, in this case, you can use the integration by part formula, and then gather this term with a symmetric one to simplify as we're going to see. But in any case, we get this theorem. This theorem about the convergence weight of this Milshtein scheme. It says it. If mu and sigma belong to C2B, that is twice differentiable, continuously, twice continuously differentiable and bounded. So by this way, the idea is just to get very simple bonds for these quantities. Okay, so that when we want to compare the solution of the SDE as an approximated one, then the idea behind is to use Taylor approximation of the second order. Okay, this is the idea. Then for all p greater than 1, there exists constant C equals C of P capital T mu sigma and D, sure, exactly. All the parameters except actually n, so independent of n, such that the maximum of all I equals 0 to n of the expectation of absolute norm in general actually S n ti minus S ti power p over 1 over p is less than C over n. That is, as you can see, the convergence rate is significantly improved. Okay? Actually, to show this, we just repeat all that we have done last time. Actually, this is very long to write it, but just write it. Okay? We have spent a long time to get such inequality last time, but with very classical techniques. It's mainly based on the grand wall lemma.
As usually in this field of problems, the grand wall lemma is used quite frequently in this.
Indeed, because kind of, I think we may relate this on lemma to the Picard iterations, which is also used for getting a solution of SDE or VSDE. It's a kind of fixed point inequality. Not fixed point, yes, we can say this as implicit inequality, sorry. Okay? Okay, so an interesting remark in general. Difficult to simplify this. Okay, it is difficult to simplify this extra term. Okay. this extra term because a priori it depends on the whole trajectory, the quantum motion between ti minus 1 and ti. Okay? But in the case where we suppose that this term is symmetric, that is the gradient of sigma ig SNTI minus 1, not I, sorry, dot sigma dot k, in general, yes, just write line or some x, you have to write 2 points, okay? X equals just the same thing, but with here just terminate k, I guess. Yes, exactly. K of x sigma dot j. If you have this, then what can you do? You can gather the symmetric terms, factorize by this common factor, okay? And then you may simplify. Because once you have factorized by this common term, you just need to compute a sum. Which sum? The sum integral from t minus 1 to ti of wsj minus wti minus 1j dwks plus the symmetric 1 wks minus this one dwjs. And for this, you use integration by part formula I recalled previously. So you get the product between the increments actually of the two processes between ti minus 1 and ti. That is SSV delta wj ti times delta w k ti minus the quadratic bracket between the two processes, which is 0 if j is different from k, and delta ty otherwise, right? So we can say minus delta ti times what I called delta of I equals for I j equals k, okay? Which means 0 except and 1, okay? You know this notation, okay? 0 if j is different from k, 1 otherwise. So that now you can simplify this, and that means that this expression depends on the values of the Brownian motions at times ti, and this is the values you simulate actually.
Yeah, it was my question. If you have now this symmetric solution, then how to simulate?
Yes, so maybe I can remind what we have seen last time. Actually, we have we have made some practicals about these techniques. And indeed, once you have such a scheme, the only thing you need to do is to simulate independent increments of the Brownian motions. The same thing here, okay? So only independent increments of the Brownian motions at the discrete times ti, that is, in other words, independent Gaussian distributions. Exactly. So this is the interest of the method. So I'm gonna stop here about the Milshtein scheme, and now I'd like to talk about the most important part of this second lecture part. This is about computation of pricing of barrier options. Okay. So. So in finance, in the case where there exists a risk neutral probability measure, we want to compute the price of some option as the expectation of the discounted payoff. And so it is what we have seen last time, in particular for European options. So for now, we're going to see the barrier options. So definition. 5.1. The barrier option is a contract whose payoff is of the form sorry, I'm thinking about the payoff function of the form G of S capital T, that is like European option, but conditioned to the fact that we cannot get outside some domain, like tau greater than capital T, where tau is a stopping time, precisely the first instant in 0 capital T, where the price process ST goes outside some domain D, of course, equals plus infinity otherwise. Okay, so this means that in this contract you can get this wealth if and only if the price process remains in some domain which is specified in your contract. For instance, you can think of some bounding domain. That is, if S is larger than some cap, then you can get anything. Okay? So, otherwise, where D is a Borel set of RD. So, this is the exit time of the domain capital D. Okay? So, as usual, in pricing, actually in classical pricing, we need to be very careful because, as you know, it's very, very classical theory, okay, provided that there exists a unique risk-neutral probability measure, then in this case you can talk about a single price for such a claim. But in general, as you know, there is no replicating price, but super replicating prices in general. So I dare say classical pricing theory we want to compute the expectation of this payoff because the price of this claim appears to be the discounted, the expectation of this discounted payoff. Okay, so this is classical and actually under the risk-neutral probability measure. So that in this problem, we assume actually that the drift equals 0. Okay, to simplify. So how to do it? Actually, last time for European options, so reminder, for claim G of ST, okay, where G is a Borel function, which is Lipschitz. This is very simple because we just approximate this claim by the discrete, using the discrete discretization of ST. That is, we approximate this expectation by the expectation of G of S and T, right? And when you compare these two quantities, that is, you want to have a hint about the error you make by approximating this by this, okay? Then you use the fact that G is Lipschitz, so that you get constant times the expectation of ST minus S and T, and you know, because of the classical results we have seen, this is less than capital L times a constant over square root of n, meaning that actually, provided that you choose n large enough, then this quantity is a good approximation of what you want to estimate. This means that you're gonna simulate a large number of trajectories of Sn, and then using the large law of the law of large numbers, you deduce the expectation. Okay, so there is a first error because of the discretization, and the second one because of the law of large numbers. Okay, so now the idea, of course, is the same. Here we use the same idea. With what is the difference? The difference is that now we need to approximate this. And so, naturally, we approximate tau by tau n, and tau n is a corresponding exit time for the discretized process. That is, tau n is the infimum, the first instant ti of n, where the discretized process Sn ti gets outside the domain. Okay? This is very natural. So now if we want to obtain such a bond, because we need to control the errors, natural, we need to make some assumptions about D, okay, to get something. So we're gonna work with some rather smooth domain capital D in the following sense. Definition. 5, 2. We said that the boundary, we said that, sorry, I'm thinking of what I'm going to say after. I see we said that the boundary is okay. The boundary of, sorry, I did not this. The boundary of capital D of D is C3 is a classical notation to say that this is differentiable to the third derivative. Okay, is if the following conditions hold. Precisely, for every point on the boundary, there exists a neighborhood Vy of y neighborhood of y phi mapped from Vy into Rd, which is a diffeomorphism. Such that, so diffeomorphism means that phi and phi minus 1 are continuous. The definition of diffeomorphism, but here actually we suppose that phi and phi minus 1 belongs to C3. That is in the classical sense, that is an R 3 times differentiable. Okay. And at last, and so this is very technical actually, and phi of Vy intersected with D is included in a half space. It is a set of X, so that we can, without some generality, suppose that this half space is of this form, because we can change phi is necessary. So this is a half space. And at last, the most important is this. That is actually this condition. That is means that you can think of the boundary as a subspace with one less dimension, because this corresponds to the set of all x such that x1 equals 0. Okay. So under these very technical conditions, actually the most important is here. And under these very technical conditions, we can obtain a nice result about the estimation of the error between the process S, the process Sn, but more importantly, between tau and tau n. This is here, and this is the theorem which was proven by Emmanuel Goubet. So, see the paper a weak approximation of killed diffusion using layer schemes by Emmanuel Goubet from Paris, Polytechnique Paris. Emmanuel Goubet. So this is a paper in stochastic processes and applications. I can give the reference if you are interested in. 2000. Okay? So the result is the following. If capital D bounded, and the boundary is sufficiently smooth. If the coefficients are also sufficiently smooth, so many conditions actually to say something. And at last, if sigma is strictly uniformly elliptic, that is for every z sigma prime z is a quadratic function defined by sigma. Sigma is a matrix, sigma prime is a transpose of sigma is greater than some epsilon norm of z square.
Z prime.
Yes. Okay, so like this. Because I will write.
Usually,
yes, in this sense, yes. Then, so for some, of course, for some epsilon strictly positive, okay. Then, in this case, we have an estimation of this error. It is why we say that it is a weak estimation, because in general, in the practical cases, we get a better estimation that is not the difference between the expectation, but the N1 norm. Here, this is a weak estimation. Okay? The strong one is the same, but we consider the N1 norm, the expectation of the absolute value, the difference between the pairs. Okay? So we get the following. Precisely for every bounded payoff Borel, of course, Borel payoff function G vanishing, so many around the boundary of T, okay, or the neighborhood of the boundary, then you have this estimation, expectation of G of S n capital T indicator function of tau n greater than T. Minus expectation of indicator function this, okay, G S T less than c over square. Okay? And actually, of course, the difficulty to get this result is about the convergence of this indicator to this one. And then, why we need such difficult, such technical conditions is about, in particular, the process S, because a priori, as S is continuous, we may think that it's gonna go outside the domain, passing through the boundary. Okay? Of course, this is not too much important because G vanishes around the boundary, so we do not mind, except that we want just. So the problem is actually to think of the problem as if there is D, there is a subdomain here, and then another one here, because G is 0 here, and so the problem is, okay, G. We are mainly interested when the process is either here or here. Okay? And then we need some information about the distance, about the boundary with this, actually. This is the idea, but this is very difficult. But actually, as you can see, this classical result, in particular, the convergence rate is very classical. But it appears that we may significantly improve this result using another technique based on the Brownian motion bridge. And this is what I like to expose, maybe now or next time, I don't know what time it is.
10 minutes.
10 minutes. So maybe I can just present for next time.
Thank you.
So actually,
excuse me, so I didn't get why you need this condition, G vanishing around boundary of D.
Actually, the problem is
you explained, but I didn't get it.
This is difficult to explain in a few words.
It's not so easy.
No, because the problem is this, about the convergence of this indicator function to this one, once we have discretized S.
I understand.
Okay? So, of course, S...
Another question. If this condition doesn't hold,
we can,
then nothing
we do not know what to say. Actually, this is very recent, and what we can say about all these things around Monte Carlo method is then paper after paper, there are some new results by trying to relax the conditions, but that appear to be very, very technical with more advances. So it's not so clear, actually. There is no, how to say, a very global view about these problems in general, actually. And we're gonna see, for instance, in the following lecture that we can say something easier, for instance, when D appears to be a half plane, for instance. In this case, we can simplify the things, but we do not have general results. Just some specific results because of technical hypotheses, we may simplify the things. This is the idea. And so, just in a few words, we may prove the convergence rate using what we call the bridge simulation method as follows. So we introduce the stopping time tau n associated to the continuous time version of Sn. Okay? Tau n is the infimum of all t in 0 capital T, such that S hat and T does not belong to D. Tau hat n, okay? So this is the continuous time version we have introduced. And then, I just formulate this result which is better, and then next time I'm gonna prove this part of this result actually. So this is a result in the paper Euler-Skins and half space approximation. For the simulation in domain, still by Emmanuel Gouvet. This time this is in the following journal. So, 2001. So here we suppose that D the half space, for instance, in the real case, just think of cap option, capital D just maybe a cap, okay, a bond. And then suppose that mu sigma belongs to C5. Of course, it's very restrictive, but yes, but actually, I think we can extend this maybe by approximating these relations, but that's not so clear. And sigma is strictly uniformly etic on D. Then, for every bounded Borel function G, such that G equals 0 around the boundary. This time we have this approximation, the indicator function. So as previously, G of S and T, indicator function of tau n greater than T, G, S and T, minus, without absolute value, okay, this is the quantity we want to estimate. This is the approximation equal some constant independent of n over n plus something which is negligible. Okay, so in this case, of course, we prove the convergence, right? That is, we get n instead of square root of n. And yes, sorry. Okay, so
and downhill.
So here, yes or not, we don't mind here because at time with activity or something.
But here, in the heuristic function.
In here it's okay. Here,
Yes.
And we're gonna see actually that we can we need to. So of course, because of this result, we need to compute this. Okay. the problem is about the computation of this indicator function, because we only observe values of S hat n at the discrete times. So this is a problem about this. But actually, we're gonna see this expectation as the expectation of the conditional expectation of this, knowing the value S hat n at the discrete times ti. Okay? So this is equivalent to actually compute the expectation of something which only depends on the values of S hat n and that's ti, provided that this new conditional expectation may be explicitly given. Okay? And this is the case because once you have conditioned this variable knowing the values of this at depth ti, then you know that this continuous process is mainly driven by independent Brownian motions. Once you have fixed the initial value at time ti-1 and the depth ti, it is equivalent to say that you have fixed the values of the Brownian motion driven this process between the two depths. But this is a Brownian bridge. This is the idea. Okay? This is what we're going to see next time. Thank you.
Thank you. Questions? Any questions? May I ask the first question? At the beginning, at the first part of your report, you suggested the idea where you use the Taylor expansion and the first part, the first term.
Yes.
If you take the second,
You can
you can do it, but it's technically quite complicated. Yeah?
maybe about the drift. You mean
No. You approximate your sigma.
Sigma.
Yeah.
of
You
SU.
approximate it by using Taylor expansion.
Yes, like this.
And take only one.
Yes. Okay.
If you take the
You
second,
can take it, but there is no interest, in the sense that you how to say? I have to explain this. I understand what you mean, but by this way you cannot. This is a good question, actually. Of course, understand this. Because you think that by this way you could get a better rate of convergence. But
maybe it's
not
realizable. I don't.
you can do it, clearly, but you cannot expect to improve the convergence rate.
Really?
I can say that because I worked a lot about this kind of schemes for other reasons in a financial market with proportional function cost precisely, and this is the same problem in linear techniques. And unfortunately, you do not
Improve the convergence.
No. Unfortunately, no.
And the second question, the barrier options. Are they really? Are they really exists in reality? Barrier options.
I think so, but they are very simple in general. It's just a payoff conditioned to the fact that S must be bounded, for instance. That is,
So in reality, such options are considered. Yeah.
Yes.
Thank you.
There is a simple payoff actually which exists. This is this one. So okay.
Okay, I understand. Okay, thank you.